Hi dear students, today we have come with a new part of class 9. In the previous part we have discussed about a new chapter, that is sound. So the introduction portion is discussed. Now we'll go for the next part, and mainly it is known as speed of sound in different medium. So before starting the topic, I just want to give you a disclaimer that in this topic, I will be going to use some of the equations which may not be known to you, and I'm not give you the reason that from where the equations have come, because that equations are there in class 11, and whenever you will be in class 11 then you will easily come to know. Okay, now whenever we are talking about speed of sound in different medium, I'm just making you remember the characteristics of medium for which a sound is needed to be propagated. So first characteristics is that the medium should be elastic. What does it mean? I have explained that time that by application of force, if the shape of a body is changed, and when we withdraw the force, if the body gets its own shape, that property of a body is known as elasticity, and that body is known as an elastic body. Okay, so here this elasticity plays a very vital role on the propagation of sound. We all know that for the propagation of sound we need a medium. So the medium can be solid, the medium can be liquid, and the medium can be gas. Okay, for every case this elasticity is needed. Okay, that means when the sound propagates, the particles may displace from its position, but after the propagation of the sound, the particles will get back to their own position. Now this property, this elasticity, we have to justify by a number, or by a value, or by a physical quantity, and that physical quantity is known as modulus of elasticity. So for yourself only you have to remember that modulus of elasticity is a physical quantity which represents the elasticity of a medium. And here modulus of elasticity we have taken E. Okay. Now coming to the second point. In the second point we have told that medium should have a inertia. And when we are talking about inertia, we are just going towards the mass. That means the particles in the medium should have a definite mass. Okay, so here whenever we have to find the speed of sound in different medium, so in that case whenever we are talking about mass of the particles, that also plays a very important role in the speed of sound. But the problem is that whenever we are finding the mass, we have to give a definite volume, because if I increase the volume of the medium, then automatically the mass will be increased. So that value should be varied if I change the volume. So instead of taking mass here, we have taken mass per unit volume. And we all know that mass per unit volume is none other than density. So the second part we have to represent by another physical quantity, density, which is denoted by rho. Okay, it is known as rho, R-H-O. In some book, density is denoted by small d also, but Nowadays it is denoted by rho. You have to remember this thing. So the speed of sound through a medium, that depends on this two things. Now you might be thinking, sir, there is another point. So we have told that medium should be frictionless. Yes, that is also one character, but frictionless, that we cannot able to represent by any physical quantity. We can represent the elasticity of the medium by the term modulus of elasticity, and the mass or the inertia, that can be represented by mass per unit volume, that is density. So using this to, whenever we have to find out the speed of sound, that value will come v equals to root over of E by rho. That means modulus of elasticity by density, its root over, that should be the speed of sound in a medium. Now you might be thinking, sir, from where the equation has come? I know that questions are coming to your mind, but I'm telling you one thing, because I cannot explain whole the thing here, but because this one is explained in class 11 properly, because to understand this equation you have to learn more things. But here you have to remember one thing, that this equation comes mostly experimental basis. Okay, so experimental basis means we cannot able to do the experiment. We can take the result of the experiment. We cannot able to make the experiment. We cannot able to arrange it. So as per experiment, we can show you that the velocity of sound through a medium, or the speed of sound through a medium, is equals to root over of E by rho. Okay. Now, this modulus of elasticity, that is denoted by E, in case of solid, this modulus of elasticity, that is E, is known as Young's modulus, which is denoted by Y. That is another surprise for you. Now you might be thinking, sir, what is Young modulus? From where it has come? There is no logic here. You are telling what is from where, no logic, why it is coming. Young modulus I can explain little bit. Okay, because if I explain, then it will be easier for you. How the modulus of elasticity has come. Assume one rod is given to you. Its length is L. Okay, now whenever I am applying force of F here, then this rod is little bit of elongate. Okay, I am applying force, then it elongates. How much? It is taking delta L. Okay, now we are assuming the cross section of the rod, that is A. Clear? Cross section of the rod, that is A. Simple thing, a rod is there, it is just fixed at a height. We have given a force at down, that's why the length is increased. Okay, how much? Delta L. Now from here we have defined two quantity. One is known as stress. What is stress? Now stress is basically force per unit area. That how much force you have applied per unit area, because the area of cross section is given of the rod. So force per unit area, that is known as stress. It is a quantity we have derived. Another quantity we have derived, that is known as strain. So strain is change of length by original length. Change of length means how much length is changed? Delta L. What is the original length? L. And the ratio of, that is known as modulus of elasticity. Modulus of elasticity is nothing but stress by strain. And for solid, it is denoted by Y. because one great scientist named Young, okay, Young has derived this thing. So it is known as Young's modulus. So stress means how much? F by A, and strain means delta L by L means it will come here. So that is Young modulus for solid. Okay, so this thing you will learn in class 11. I'm just giving you a hint how we can able to find Young modulus for the case of solid. So if solid through the solid sound is propagating, so in that case the modulus of elasticity E, that should be taking as Young's modulus. If you are not able to understand why we have done this, no need to be panic. You have to remember this thing. Okay, what the things you have to remember that I have written, these things are not needed for you, that is for your knowledge. In case of fluid, fluid means both liquid and gas. That E, that is modulus of elasticity, I am not writing the whole thing, should be taken as K, where K is known as bulk modulus. BULK modulus. Okay. Now another question. So bulk modulus. What is it? I'm just giving you a little hint, though it is not needed. Assume it is a block given to you. Okay, three-dimensional thing. You are applying force from everywhere. Okay, and the cross section is A. Okay, you are applying a force of F from everywhere, and due to that, its size is changed. Okay, initially it is so much big, now it is changed to a smaller block. Now in this case, we can able to find the stress. So the stress will be force per unit area, just like the previous thing, and assume the initial volume that is equals to V. Assume initial volume of the block, and now whenever we have taken the small block, now the volume is V minus delta V, because the volume is decreased. Initially it is V, now it is V minus delta V. So delta V amount of volume is changed. So in that case, strain, it will be equal to change of volume by original volume. Here it is change of length by original length. In this case, change of volume by original volume. Clear? So in this case, if this thing is occurred, so here also we can find that modulus of elasticity, that is known as bulk modulus here, that is F by A delta V by V. So V will come up. See, F by A, we have learned earlier that by the application of force on a surface area, force per area whenever we have to find out, that is basically pressure. Force per area, which is denoted as a stress, so it can be taken as pressure. So F by A, if we denote it by P, so it is PV by delta V. That is known as bulk modulus. Okay, so whatever the things I have discussed here, I think more than that it is not needed. Okay, so this Young modulus and bulk modulus is also not needed for you. For yourself, the knowledge you have to keep that the speed of sound, that should be root over of E by rho, and whenever we are talking about the speed of sound through solid, we can write it Vs, that should be root over of Y by rho, and whenever the speed of sound through fluid means either liquid or gas, then it will be root over of K by rho. And these equation has come experimentally. Okay, so don't be panicked from where the equation has come. These are experimentally coming. Okay, now we'll go for next thing. Next thing, based on the speed of sound, that is, so you might be thinking, sir, you have written Newton's law. So whether we are discussing about the motion in straight line or motion in one dimension? No. Newton, Sir Isaac Newton, who is a great scientist and who has researched about all the things in physics, we can say. So everywhere, if you're finding out, then you can find a law of Newton. So let's see what Newton has told here. Newton has told the propagation of sound through a gaseous medium is a isothermal process. So you might be thinking, sir, what is it? Isothermal process? Isothermal process means, I have mentioned here, isothermal process means the temperature of medium should be constant. That thing also you have to learn in details in class 11. So you have to just remember this thing, that Newton has told the propagation of sound through a gaseous medium, that should be isothermal process. That means whenever the sound propagates through the medium, that time the temperature of the medium should be constant. There should be no change, isothermal, I'm sorry. There will be no change in temperature. And we have already learned that the speed of sound in gas, that means in fluid, that is equals to root over of K by rho, where K is bulk modulus and rho is density. Okay, so temperature of the medium is constant and equation is this. Newton has calculated one thing. What is that? Now, whenever we have told that a process is an isothermal process, so that one you have to learn in thermodynamics in class 11. Maybe in class 9, 10 you will get a little hint about that, where you have to learn little about ideal gas. Okay, so for isothermal process there is an equation that is known as equation of isothermal process. If you have not known this, no problem, it is not needed also. That is PV equals to nRT for the case of gas. Okay, what it represents? PV equals to nRT, where P, it is the pressure of a gas, V, it is the volume of a gas, N, this is known as mole number. I think you have learned about mole, molar. Okay, so it is mole number. R, that is universal gas constant, and T, that is the temperature. So that is the equation of isothermal process. So what Newton has told? That Newton has told that as the propagation of sound through a medium, it is isothermal process. So he has applied that law into this equation. How it is applied, that I will not show. Okay, that is a part of class 11. But whenever it is applied, he has shown that bulk modulus is equal to the pressure of medium. So Newton has calculated this thing. Okay, how? I'll not show it here. You have to remember this thing. That means the value of K, it will be changed to P. as per Newton. We can write here after calculation. Okay, so if I replace P with K, then what we will get? Now V, that means velocity of sound through gas, it will be P by rho, that is pressure by density. That is the value what is taken by the great scientist Newton. Okay, now what Newton has done later, now the atmospheric pressure in sea level we know, that is almost P equals to 1.015 into 10 to the power 5 Newton per meter square. That is the common atmospheric pressure in sea level. Okay, and if I'm talking about the density rho is 1.293, that is kg per meter cube. If you ask that whether we need to remember this thing, I will say no, it is not needed. No need to remember the whole things. Okay, that is the experimental value. So if we put the value here, we see the velocity of sound has come. It is around 279.5 meter per second. This result has come by Newton's experiment. But there is a problem, because experimentally it is shown velocity of sound that is around 330 meter per second in gas, means in air. But if I put the values, that is the density of air and the atmospheric pressure, the value has come to 79.5. That means the Newton's law is not correct to find the speed of sound. That means there must be some problem. Okay, now you might be thinking, sir, if there is problem, then why we are doing this? Because if we don't know the problem, then how it should be solved? So to solve the problem of Sir Isaac Newton, one another scientist has come. Okay, and whose name is Laplace. Okay, and the thing he has shown, that is known as Laplace's correction of speed of sound. Laplace's correction of speed of sound. Okay, what correction he has made? Newton has told that the process by which the sound propagates through a medium, it is an isothermal process. That means the temperature should be not changed when the sound propagates through the medium. Laplace has told no, the process is adiabatic process when the sound propagates through a medium. Now you might be thinking, sir, again another process? Yes, it is adiabatic process. What is adiabatic process? So you have to remember a little bit that adiabatic process means the heat energy will be constant. Previously it is told the temperature will be constant, no change of temperature, and here Laplace has told temperature may be changed but heat energy will be constant, and you all know that heat and temperature are not same. So by this little confusion that heat and temperature, how the value is changed, let's see. So in adiabatic process also we have taken one equation. Obviously that equation also you have not learned, but here I have just written that equation. Just see, No need to memorize it, no need to remember this, just to see that what is the equation of adiabatic process. It is told as PV to the power gamma equals to constant. So in this equation, P obviously it is the pressure of the medium, V that is the volume, but gamma that is a new thing. What is gamma? Gamma it is told as it is the ratio of specific heats in gas. So what is specific heat? Everything you will learn later. Okay, so you might be asking, sir, if we everything we have to learn later, then why this thing is given here? To tell the truth, I also don't know why this thing is introduced in your book, because this thing cannot be explained if you have not learned about thermodynamics, and that you will learn in class 11. So better we can learn it class 11, but as it is given, we have to do it. Just remember, specific heat, it is a property. Every body, every particles or every element has specific heat. But for solid and liquid, it is have only one specific heat. But for gas, there is two specific heats, Cp and Cv. Okay. So Cp, that is known as specific heat at constant pressure, and Cv, that is the specific heat at constant volume. Okay, so you have no need to remember this thing, just to see that gamma is the ratio of specific heats in gas. And when this value it is put in the equation, that is V equals to, that equation we all know, that V equals to root over of K by rho, all that things it is done for the propagation of sound through gaseous medium. Okay, when it is put here, then we can write, after calculation, the value has come K equals to gamma into P. That means bulk modulus, initially it is equal to the pressure, but now it is equal to pressure which is multiplied by a constant term, that is gamma. That is the ratio of specific heats. So if I put the value of the velocity of sound, that should be root over of gamma p by rho. And if I put the value here, where p equals to 1.015 into 10 to the power 5 Newton per meter square, if rho equals to 1.293 kg per meter cube, and gamma in air it will be 1.4. If we put all the things here, it is coming 330.7 meter per second, which is almost equal to the experimental value. Okay, so we can conclude that that is the ultimate equation by which we can able to find out the speed of sound in a medium. If I know the pressure, if I know the density of the medium along with the ratio of the specific heats, that is gamma, then we can able to find the speed of the sound. Okay, seems to be very hard, but it is not so hard. You have to remember it as a story. No need to memorize all the things. So don't be panic. Next thing we will learn that the factors that affecting the speed of sound in a medium. Okay. So whenever you have to see it to a book, it seems to be very hard, so much description. But all the things we have to describe by this equation, that is V equals to root over of gamma P by rho. And by that equation, your all the factors will be so easy that you can see here. First factor it is coming, that is density. So it is pretty clear in the equation that with the speed of the sound, the density is proportional inversely root of density. Okay, so V is inversely proportional to the root over of density. If I have taken gamma P out as a constant, that means if the density of a medium is increased, then definitely the speed of sound will be decreased because it is in denominator. If the density increase, automatically the speed will be decreased. Or in vice versa, if density is decreased in a medium, then automatically the speed of the sound will be increased. Very clear. Density increased, speed decreased. Density decreased, speed will be increased. Okay. Number two, that factor is also very important, that is temperature. Okay. See, whenever we just increase the temperature of a medium, then what will happen? Now you will tell that as the temperature is increased, the volume will be increased. We all know that. So you might be asking, sir, in the equation of speed, there is no story of volume. Then what will happen? As the volume is increased, we all know density will be decreased. How? Because we know density rho equals to mass by volume. So if the volume of a medium is increased, then definitely this denominator will be increased and the density it will be decreased. And we all know the previous story. If the density decrease, then speed of sound increased. So we conclude that if temperature increased, the speed of sound increased, because the whole story just lies inside it, that as the temperature increased, then the volume increased and density decreases, so the speed of sound automatically it will be increased. But here we have to remember some equation. It is told that then the speed of sound is directly proportional to the temperature, root over of temperature. So here T, as it is written in Kelvin. So if the temperature is in Kelvin, then V is directly proportional to root over of temperature. Kelvin means in Kelvin scale. And if the temperature in degree centigrade, then the equation will be Vt, that is equals to V0 plus 0.61 into T. What is Vt? That is speed of sound in T degree centigrade, and V0 speed of sound in 0 degree centigrade. Okay, so definitely as it is added by this fractional term, so if the temperature is increased, then also the speed of sound is increased by following this relation. Now you might be thinking, sir, from where the relations has come? I'm very sorry. That also you have to remember. I cannot able to explain here. That is also a story of class 11. You have to remember these two equations, and above all you have to remember one thing, that the speed of sound is increased with the increase of temperature. That is the only thing you have to remember from here. Okay. Now we are going for the third factor. And third factor is also anyhow, it is correlated with this. What is the third factor? The third factor is humidity. So nowadays you all know it's raining too much. So now the air it is humid. So that's why we are sweating continuously. Almost everyone. Okay, if we go outside, we are sweating. Okay, so that's why we told that it is a humid weather. But one interesting thing, humid weather means in that atmosphere the amount of water vapor is increased. So you might be thinking, sir, water vapor is increased in atmosphere, so maybe the density of the medium is increased. No, here the twist is there. As the water vapor is increased in a medium, the density of medium decreases. If the medium is dry, means less humidity, then the density will be more. If the humidity is increased, that means water vapor is increased in a medium, then the density of the medium is decreased. And we all know, as the density decreases, speed of sound increases. So we can conclude that the speed of sound increases with humidity. So more humid weather, more the speed of sound in a medium. Okay, it's a very easy thing. Coming to the fourth point, that is direction of flow of wind. So that one is little obvious. So if you have not told also, by your common sense you can understand that in which direction sound move. Okay, so if I show the sound moves in this direction with a velocity vs, if the speed of wind also in same direction, that is v of w means speed of wind in same direction, then definitely in this case speed increases, means the speed of sound it will be increases. And assume if the speed of sound is in this direction, means you are just want to propagate the sound in this direction, but the wind is propagating in opposite direction. So definitely the speed of sound decreases. So it is quite obvious. So if the speed of sound here Vs, so now the speed of sound will be Vs plus Vw, as the two directions are same. And in this case the speed of sound Vs, it will be decreased, so it is Vs minus Vw, it will be decreased there. So I don't think you have to remember this thing, it is quite obvious and you all know that. So these are the factors on which the speed of sound depends. Whenever we are discussing about the factors that affecting the speed of sound, we have to mention one more thing, that factors that not affecting the speed of sound. What are the factors which not affect the speed of sound in a medium? Okay, that also we have to see. First one, which is very much surprising, and you also think that whenever I have to write down this thing, you also quite shocked that why this thing is here. Pressure. Whenever I have to write this thing, the things it is coming to your mind, so the speed of sound Vs, that is equals to root over of gamma p by rho, and you have told it is the equation which is followed by the sound in a medium, and that equation is derived by Laplace. So now whenever we have to mention factors that not affecting the speed of sound, at first thing you have written pressure. How? Because here we have seen that if the pressure increased, obviously the speed will be increased, because it is a directly proportional relation is there. But here the twist has come. Simple thing, as pressure in a medium increases, just feel the things whatever I am writing, as pressure of the medium is increases, pressure you have increased it, then volume decreases. If pressure increased, so definitely the volume will be going down, the volume will be decreased. Okay, so if the volume decreases, then density increases. See the link, pressure is increased, that's why volume is decreased, and if the volume is decreased, the density is increased. So then the ratio of P by rho should remain constant. Why? Because if P is increased, we have seen the rho is also increased. Similarly, if P is decreased, rho is also decreased, because if pressure is decreased, then the volume will be increased, and if the volume is increased, then the density decreased. See the relation. That means as the pressure increased, the density increased. As the pressure decreased, the density decreased. So here we have seen there is a ratio of P by rho. So if pressure increase, the whole ratio will be unchanged. So we can say as the ratio P by rho is unchanged, so pressure will not show any effect on speed of sound. So interesting thing. It is a part of the equation, but it doesn't affect the speed of sound. Okay, so it is also experimentally proved. So that is the first factor which doesn't affect the speed of sound in a medium. Second factor, amplitude. We all know amplitude is the maximum displacement in a medium. Okay, the vibration of the particles in a medium. So amplitude, it doesn't affect the velocity. We also know that it doesn't affect the wave velocity no more. So if the amplitude is also changed, means if the sound is louder or if the sound is not louder, it is softer, then also the speed will remain same, because louder sound and softer sound, that is explained by amplitude. Louder means more amplitude, softer means less amplitude. So in both the case, the speed of the sound will be same. Okay. Coming to the third thing, and it is also a little bit of shocking for you, that is frequency and wavelength. So you might be thinking, sir, just in the previous class we have seen that the speed of sound depends on the frequency and wavelength, that is V equals to F into lambda. So you have told here there is no effect of speed of sound. One thing I have mentioned here, that frequency and wavelength, this two property depends on source of sound. Okay, these two properties, both the properties depending on the source of sound, and here we are discussing about the factors when the sound propagates through a medium. So if a sound just comes from a source with a certain frequency and wavelength, that will be not changed when it is propagates through a medium. And our discussion, our whole discussion, this speed of sound shows in a medium. So here, as they are depending on the source of sound, so they will not give any effect when the sound propagates through a medium. So these are the factors that are not affecting the speed of sound. Okay.